Recording, Yogesh. All right. So I'll have to close few things. Good. All right. Great. So yesterday we talked about this new framework called Apache Spark, which is apparently competing with MapReduce. Also, this framework is fairly fast and is basically there is a design changes whereby it's trying to utilize more of RAM than the disk. So it's not that all the data gets loaded in the RAM. It's just in the judgment part when doing any computation, it tends to load the data in the RAM from the available memory. Okay, so that was the design thing, and then we talked about the general architecture. So I'm just doing a quick recap for everyone. So then we talked about how it basically can connect to all kinds of file systems because Spark doesn't have its own file system. And just like MapReduce, it runs on top of another resource manager like Yarn. And it can also run on other resource managers other than Yarn, such as EC2. Mesos is another resource manager and standalone. Resource manager is somebody who keeps a track of all the computers connected in the network, which one is free, which one is busy, if there is a work, who should we send it to. So the usual task tracker and the kind of discussion we had about task tracker and job tracker. Similarly, we also talked about Yarn when we discussed about resource manager. So all right, so Spark can run on different kind of resource manager, and if you don't have an existing resource manager, you don't want to install any resource heavy weight resource managers like Yarn, then you can use Spark standalone, whereby you install it comes with its own resource manager, which we call standalone. All right. So Spark contains many kind of libraries, starting with streaming, for MLlib, for GraphX, and you as a user can interact with Spark either via SQL, Spark R, Java, Python, Scala. So you have different kind of APIs to talk to in different language. All right. So now, getting started was very simple. We are going to talk about how to access Spark in Python. Why? Why do we prefer Python over Scala? Because number one, Python is far more simpler than Java or Scala comparatively. And number two, since Python is a quite popular language for any data related developer or data architect, or Python is quite popular amongst data scientists because it has many libraries to manipulate data. Therefore, we choose to keep our discussion around Python when interacting with Spark. All right. So I hope. All right. So, do you have any questions at this point of time? A question from Ila. Are GraphX and MLlib part of the Spark installation? Yes, they are part of Spark installation. And for that matter, we have installed the other libraries related to Spark. Okay. Now coming back to what we had discussed. So, all right, good. Now, there is something called RDD. RDD is basically a data set. And it's very important to note that any data related language be it SQL. In SQL, there is a representation called table, and we all must be aware of table, right? Similarly, when we talk about Microsoft Excel, the the idea of a sheet in which there are many rows which you keep inserting. Similarly, in a database, you have the idea of a table, and in R, you have idea of a data frame. So almost every data related language, for that matter, when we talked about when we talked about big, there is an idea of a data set. So almost every data related language has a construct that represent a array of the data. And here in Spark, that array is called RDD, Resilient Distributed Dataset. This dataset is basically not always all the data loaded into this dataset, but this dataset is kind of a relationship between the actual data and a array. The way in an array you have pointers to external data, similarly RDD sometimes contains actual data and sometimes contain the pointer or the information about actual data. So an RDD, the way you look at an RDD is it's an array of records. A record can be individual object or any complex object, or array could be a key value kind of object. So, or array could be a primitive. The individual value could be primitive like number or a string or maybe numeric. So the way you can visualize an RDD is it's a huge array of values distributed across the cluster. For you, it's like an array, and if you look at from the system internal perspective, it's basically small arrays on many machines. Okay, for you, it's basically a singular array. Managing the complexity of which part of the array or which partition, we call them partition because the array is divided on many machines. So the part of the array on an individual machine is called partition. So the partitions of RDD are located on individual machines. So from time to time, if you need an RDD again and again, you can persist it in the memory and you can also save it in the disk. This RDD can recover from failures, and because Spark knows about how we created this particular partition or particular RDD, and it can again rebound the whole process, rebound the array by executing the whole process of creating an RDD. So the quick way of creating an array or RDD is this. We can simply convert an in-memory array into an RDD by simply saying sc.parallelize. I'm going to open no big data and then we are going to. Any questions at this point? All right, let me open my notes. Okay. Today is 29th. Good. So question from Ila is, to confirm array and RDD are also, let me just keep it here. Array and RDD is a mapping of source system. Yes. So sometimes it is cached in memory data and sometimes it's just a mapping from the actual data. So that internally is managed by Spark for you. All right. Just the way in Java you don't have to deal with pointers. Similarly in Spark you don't have to deal with this mapping of the internal memory. But you can say that please cache my data, don't bring it again and again from the server. All right. Now, also I can open CloudX Lab. You can also open CloudX Lab, and from my lab here, my lab, you will get all the details, actually more details than the available in the no big data. So here you see lab credentials, and these are the services. Okay. All right. Is the font clear to everyone here in the terminal? Because it's very important to observe what I'm doing. So, all right. So right now, by typing PySpark, py spark, I have started the Python console, which connects to Spark. This Python console is connected to Spark, and whenever we have to interact with Spark, we can use SC as the entry point. So first thing we are going to do is, all right, let me try to load this data in the memory, or better, let me try to load this data in the memory, or okay, I actually don't need this whole process. By default, any file path you use here, any file path you use here will talk to that particular machine. Okay, so similarly here, so either you can refer to the text file. If there is an external HDFS system, you can refer to that HDFS system using this kind of a URL. Okay, and if you have your own local, if you are already on a cluster, you can simply say lines equals to, as in lines could be anything. This is your variable. Okay, let me just put it here. That will be more visible. Okay, so here we are saying this is our data set or RDD. Lines is going to be our RDD, and it's a variable name, so you can keep anything here. And we are going to say sc.text file, which means Spark context dot text file, and we're providing the URL of the text file. What does it mean? We are trying to create RDD over this text file located in HDFS. This text file is located in HDFS. So now this lines object, you can see it's a mapped partition RDD. It's basically an RDD where various partitions are mapped to various input splits are mapped to individual partitions on RDD. Okay. So now when I say lines dot say take, I'm not going to collect because it's really huge. I'm just saying bring 40 rows from HDFS to me. Now what happens here is the evidence of whatever I'm saying. So this evidence here, when I say here, you can see running the task, and then input split is this. Okay, what does it mean? Here the task is being executed to read the data from HDFS using input splits. Okay, this is what is happening right now. All right, and here are the records. Each line is an element in an array. U in the beginning of the string means the string is encoded in UTF. All right, that's a general representation of Unicode in Python. All right, so this is how a Unicode string is represented. All right, so it's the same file, same text file, which contains all the data of the Arthur Conan Doyle's Adventures of Sherlock Holmes. Okay, so it's the same file which we use for map task. Right now, the lines task, lines is an RDD. Now let us say, so you can think of some lines on one machine, some as an array, some lines on another machine, and some lines on some other machines. This is how you can visualize the whole file. Every line is an element of this big array which is located on multiple computers. So Yogesh's question is, with Python console, do we have any other Spark supported, any other Spark supported by Spark? With Python console, do we have other um, other console supported? Yes. So with Python console, there are actually quite a few. You will see scikit-learn is using Python under the hood and others. Okay. All right. Ella, as I was explaining, it's basically U means a string is encoded in UTF. Okay. It's a format of representing a string in Unicode in Python. All right. Unicode, UTF-8, not Unicode, UTF-8. All right. So that's an important part. Now, we can recall, I mean, this is a general way of thinking of every line in UTF-8 format. All right. Now, let's say we want to operate on any of these RDDs. Now, we cannot, if we try to do a for loop over lines, what would happen is, let's say we say, for every line, do something. Now, what would happen is that might become iterative, right? That might become iterative in the sense that it will bring data from line and keep on moving. Now, the way to avoid it is by using transformations. All right, I'm getting some calls from students. Just give me a second. I think somebody is not able to log in. All right, never mind. So, all right. So, is that clear, Ella? Good. Now we have. Okay. All right. Now let's move on. I think I should basically move the terminal to another window and okay, so all right. Now, so question from Ella is how do we clean them? There's no need to clean them. This is the standard way of representing a string. So we don't need to clean these to process them. All right. Next is because that's not part of the string, and it's basically a good way. Actually, it's a better way of representing a string. All right, now going back to what we were discussing. So this way we were able to load an RDD from the memory and from the HDFS. Next is, if we have to do the transformation, a clever way would be, if we want to process this data, a clever way would be to send the code to the data instead of bringing data to the node on which we are running the console or we are running the driver. Okay, so Spark is running on all the machines. Just like Spark can run on all the machine the way MapReduce can run, right? On the machines where node manager is running and resource manager would locate you the process for Spark to run on a cluster. Now, the launcher is your machine. This console is the launcher. Whatever we say, it's going to launch in a cluster, correct? So this is the Spark driver application. Right now, it is the console. From here, let's say we want to process a file. We want to, let us say, capitalize every line. Or let's say we want to convert, the first, uh, or let's say we want to make every character capital on this file, or we could do any kind of processing. So one way could have been that we bring every line from the partition to the driver, and there we process and then send it back and then save it, right? The other smarter way could be that we write this code which takes every element and then process and convert it, processes it, and then creates a new RDD. And that's what is a transformation. A transformation transforms an RDD, elements of RDD, into elements of new RDD. There are many kind of transformations. Transformations are run on every node parallel. Just like you have filter in Pig, just like you have for each in Pig, similarly, you have transformations in Spark. These transformations, whatever logic you use, it's going to run on all the nodes in parallel. All right. So that is the beauty of it. The other important aspect of a transformation is an order which Spark takes a note of but does not execute it right away. All the sequences of transformations are executed when an action is executed. When we say take or collect, then all the transformations resulting in that particular action or that particular RDD would be executed in the sequence. Just exactly like Pig. When we say dump on a data set, all the filter, group by, and everything, when all of those get executed at the time when we say dump. In the same way, all the transformations of Spark are going to get executed the moment we say call an action. So action is another kind of processing unit. Okay, so let's take a look at this particular transformation. So there are many kind of transformation. One of them is map. Map translates one element at a time into another element, correct? And filter checks whether an element is eligible to put in the output or not. And how does this transformation happen? We pass we pass the function as an argument, we pass the logic to map. So we pass the logic to map in an argument, right? Because what we are doing, instead of carrying the data, we are trying to carry the logic. So we pass the name of the function as an argument so that map can take your function to every partition in RDD and execute your function against every element of the RDD. All right, and then it'll basically, whatever is the result of your function, it will put it in a new array and call it another RDD, right? In the similar fashion, in the filter transformation, you're going to write a qualifying function. This function will qualify an element, so and only if it says that the element is qualified by saying returning true or false, only then that particular element is going to be put in the output. Okay, so what we're going to do is we will try to use these to map and filter. And there are more transformations such as flat map. Flat while while map translated one object into a single object, flat map translate one object into many objects of the array. So that's the important part of the flat map. So if you remember in our map reduce assignment, our mapper in the beginning, our mapper was printing many key values for every input. So essentially the Hadoop's map reduce was flat map, not the normal map. Here, the normal map, one input can only produce one single input, while flat map can convert a single input, single element of an array into multiple elements of the array. Okay, while filter can reduce the number of elements. Group by key basically uh, takes the objects, they thinks of every object in the array as key value pair. So in Python there is a special kind of object, we call them tuple. In Python we have a special kind of object, say this is a tuple. Okay, so x is a tuple, and so so and we can also create an object like this. So this is a set, and this is a tuple. Okay, a tuple is sequence of value just like an array, but it has a different connotation. All right, so if individual object is tuple, then the first element of the tuple is considered key, while second element is considered value. All right, so we will show you one or two examples of map, filter, and flat map, and that should be good enough. All right, and other is, okay, so let's try to run through this quickly. All right, so let's say we define a function. Let's call it to upper. Okay, and I'm writing my name. I'm a little egocentric person. So, all right, I'm going to say line dot upper, and then so I've just created this nice function called to upper sg. It takes some input in the argument and test, and it needs to return something, right? It needs to return, okay, I forgot to put return. I'm creating the other function. So the way you define function in Python is by saying def, then the function name, then the argument, and then the return whatever value you want to return. So right now we are trying to return, we are trying to, okay, so right now we are trying to convert it into uppercase. So do you see that? My plan has worked. So this function successfully converts every argument into uppercase. All right, this function is converting every argument into uppercase. All right, now so you can see that, which means the function is good. Now if we say lines, you remember what is lines? Lines is the RDD. We say lines dot map, and we say this is the function. So you can think of toUpSG as a machinery which takes input some string and converts it into uppercase. But one object at a time, it results in one object per one input object. So there is a 1:1 relationship. So you can see that. And when I say this, it is going to result in another RDD, which I'm calling uplines, uppercase lines basically. And let me try to see what's there in the uppercase lines. Do you see that? It has converted every string into uppercase. So the moment we said take 40, take 40 is an action. take is an action which takes an argument called 40, any number of lines which you want to print on the screen. So when we say take, it's going to execute all the transformations happened before this. Or other than take, you can say dump, or you can say collect, not dump, collect. Okay, so either take brings you only specific number. If you say collect, it will bring all the values into the local memory. Do not use collect, because the whole objective of distributed computing gets defeated because of this. All right. So the moment, all right. So we can say x equals to upline dot collect. Now this, the moment I say this, is going to bring the is going to bring all the values in the local files, right? So I'm saying x dot, or we can say length of x. It will tell us that it has got so many records, right? So we could say delete x. How do you say delete x? Or we could say x equals, no, or I'm just saying this. So now x is freed up. So I've deleted it so that it doesn't take any memory. So this is a bad way of doing things, because we are bringing all the data from appliance into local memory. Okay. If you do that, you might overflow the memory. So a last question is, I'm guessing that map and other transformation can take Java function as well. Yes. So if you are coding in Java, right now we're coding in Python. If you're coding in Java, you can use the whole Java philosophy. You could define the functions, and you can extend a base class, and then implement a function and pass that base class as argument. All right. So object of the base class as the argument. So that's a completely different philosophy, but for sending the data. But the basic remains that we are sending code to the data. Right. Let's say out of these up lines, so we showed you that some of these lines, when we said, where was that? Okay, it's not showing here. Here. Some of these lines, okay, let's say we want to keep only those lines whose length is greater than 10 and less than 20. Okay, let us say we have this specific requirement that out of these capitalized lines we want to keep only those lines which are greater than 10 and lesser than 15 in nature. Okay, so what we do for that, ouch, I am writing again and again. So I'm defining a function only specific, I call them 10 to 15. Okay, this is what the function name, only 10 to 15 character lines. Okay, so I'm saying argument is each line, because this function is going to be evaluated on against every element. So I'm going to say return length of line, or I can say L equals to length of line, and return L less than 15 or 16, and then L greater than 14 or greater than 9. Sorry. So all right, let me define the function again. Even though I love the Python language, but I'm still not too conversant. Okay, so let's check if it's working fine or not. Okay, so this is a line. Let's just check if it's returning true. Good, this is good. And what happens in this case? This is false. This is yet another very big line. This is also false. Good. So which means our function is working. Now if I say up lines and we say uh, only small line equals up lines dot filter. Good. And I say take, let's say I see again take 40. Now you can see here that only those lines which are 10 character or so are left. This is a line, this is another line, this is another line. Do you see that? All right. So a question from Ella is, so what about when the code has to work on terabytes of data? How is the memory overhead handled? My simple advice is don't use collect. All right, that's what I was trying to say. Don't use collect. Because collect essentially brings the distributed data into local. What I saw is when I was reviewing some people's code on Spark, that when they found that they cannot convert their logic into maps and reduces, they ended up, they silently did collect and did everything in the memory on the launcher box or the driver node. Okay, so avoid using collect, and that is my piece of advice. Okay, so whenever you are dealing with huge data. All right, so now the second piece of code that can be executed in Spark is our actions. Actions basically return, actions actually make things happen. The way when we say take, it executed things. All the transformations before an action get executed on which current RDD depends upon directly or indirectly. So when an RDD which you are calling, on which you're calling an action, if that RDD depends on 20 other 20 other RDDs, and those RDDs indirectly depend on another 20, that means 20 plus 20, 40, 40 executions will happen. Okay, so here again it's a DAG, directed acyclic graph, bit amongst RDDs. Okay, because our, okay, so our one RDD, our current, what do you call, this RDD called only small lines depends on uplines, and upline depends on lines, and so on. All right, sounds good. So an action is basically for bringing data back to the driver application and make things happen. Either it brings data back to the driver application or it saves data in HDFS. But action is a conclusive step. The way, unlike SQL, where every query has to give you the result, unlike that, an action in Spark, only actions are supposed to give you the results. Okay, action is more like executing your Spark plan. Next, so there are many actions. Some of them are very interesting. One of those actions is reduce. So reduce basically converts two values into single value, and is very important when we want to um, when we want to convert the whole array into a single value. All right. So reduce is an aggregation where it takes the function, the aggregate function. uh, it aggregates elements of a data set as in a big array, two at a time, and it converts into a single value. Now your question would be, how there is this function which so there is this function called func which we are passing to the reduce. Now this function will be executed again and again, taking two values at a time, and 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 the results of this function will again be passed through the same function again and again until we reach on a single value. That's reduce. This is classic reduce. Unlike the reduce of map reduce, where all the values were available to the reduce function at a time, all the values were available in our classic map reduce. Here only two values at a time would be available to our function, and this function is supposed to return only one value. Okay, it could do sum up, it could do minimum, it could do maximum, and so on. All right, so let's say we want to find out what is the biggest line, in the in this file, right? If in this file, if you want, we have to find out what is the biggest line. So what we'll do, we have lines, right? We define our function. Okay, we call it max length line. Okay, we are saying max length, we call it max length line. Okay, it takes two line 1 comma line 2 as an argument, and if length of line 1, okay, is greater than the length of line 2. If length of line 1 is greater than length of line 2, return line 1, right? Else return line 2. Okay, sounds good to you? Now let's check if this function is working fine. So this function is taking two lines. Let's just check whether it's working correctly or not. Good and good. So we could also say dot 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 dot. Now you can see that the bigger line is being printed, correct? And that's what we want to do as part of reduce. All right, very good question, Ella. Let me answer it after this. Okay, so we have got lines as RDD, and I say biggest line equals lines dot reduce. Now, what does reduce expect? Reduce expect a function which can compare two values at a time and give a single value. Now, it has done the work right away. Okay, and the name of the data is biggest line. You can see that this is the biggest line. All right, this is the biggest line. So great, everybody with me on this so far? So we were able to very quickly do the map reduce and use the whole mechanism from the command prompt immediately. Everyone, are you with me? So the same approach what we did just now for few MBs to find the biggest line can be done for petabyte of data and can be done very, very easily. All right. Good. So we talked about map, we talked about filter, and we talked about reduce. Okay. Let me try to demonstrate you if I can. Mm, Not this. I want to do sketch. Sketch is a small drawing application you can use. All right. All right. So how does it work? Okay. Let us say we had a big array. Okay. Let's say we have an RDD and we have two elements. Instead of XY, I'll just put the real one. Let's say we have 10, we have 15, and we have 13. So let's say we write a function called max, which takes two elements at a time. Okay, so this is our max function, and max will give us 15 as the result. Okay, now again these two values, same max function will be compared against 50 and 13 and 15, and what we will get is 15. Now the beauty of this way of execution is that you can distribute the work. How can we distribute? Imagine that we had one more number called 2, right? Now independently, so I'll try to make it smaller, and good. So here what you see is this. All right. So on these four element, max has been executed thrice, meaning n minus 1 times. And this max, if imagine that your partition, this is big RDD, it has got four element. In reality, you will get more element. So this could be one partition and this could be another partition. They could be on two different computers. This could be PC1, and this could be another computer, PC2, and where the max would be executed on PC1 while this max would be executed on PC2, and then both of these values will be brought to the node from which you are logged in, the console, and there again the third execution would happen. Okay. So this way, the work of Max is distributed. It's not a duty of a single machine. It says that execute Max on every node in the cluster, and whatever is the result, again call Max on those results from every partition and give it to a single machine. Does it make sense to you? Yeah. So this is an example of reduce. So using a simple function which takes two values and returns one value, you can translate the whole array into a single object by calling this function again and again on the result as well. Yes? Any questions at this point? Abru, Ellen, Ashwini, Ashwin, Ella? There's one question from Ella and Yogesh. Fini, Kulbir, Prem, Ravi, Ritika. Any questions at this point? Great. Now moving ahead. All right. So this is the basic operation on RDD, and using the combination of maps and reduces and actions and transformations, various kinds of actions and transformation, you could do many magical things. Okay, so when you talk about Spark SQL, under the hood, it's doing the maps and reduces on Spark, on RDD. Similarly, when we talk about Spark R, in Spark R, there's the idea of a data frame. That data frame is is essentially distributed using RDD. When we talk about in future, when we talk about MLlib, it's nothing but a distributed. So MLlib has another set of distributed vectors and distributed matrices in various ways, and all of the logic, all of the data representation is actually done on top of RDD. All right. So okay, a question from Abru is, like we discussed in a map reduce class, some actions like average may need to be done on the whole data. Yes, yes, very correct. So not every, so you are very right. Not every logic is good for reduce. I will show you this example. Okay, I'll show you this example where it'll break. For example, if we write, let's say I'm writing a function called, let me show you this. Where is my console? So let us say we have an array. We have an array called 10, 23, 2, and 13, 89, 90, and 22, and 11. Okay, so what's the average of A? Let me check. Is there an average of A? No. We can say sum of A divided into 1.0 and divided by length of A. Okay, so you can see is 31.35, right? But if we do the same thing, let's say we define average, what do you call it, average reducer function, which takes two values, x and y, and it returns it returns x plus y divided by 2.0. Correct? Sounds good so far. And let's check if it's working correctly or not. So good, it's working fine. It's working perfectly fine. Now let us say we have this array. First, let's convert it into an RDD. Let's call it array RDD. And we say sc dot parallelize A. So we are converting our in-memory array, this array, into an RDD. Okay, so this array, if we say reduce and we pass this function called average reducer, now it says the answer is 21.685. Okay, 21.685, while the correct answer is 31.375. Do you see the difference? All right. So now you can see clearly that computing average is not possible using directly. Instead, we will recursively sum and count the partitions and then do the job. Okay. All right. Good. Good with everyone. All right. Okay, before we move forward and I forget, let me answer these two very interesting questions. One is from Ella. What is the life cycle of transform RDD? Do they get destroyed automatically by Spark? As soon as your process ends, the RDD ends. Okay? If, and actually, as a matter of fact, as soon as, so an RDD gets destroyed after the work of an action has finished. Destroyed as in the in-memory computed and computed RDD gets destroyed. So when we say anything here, when we say arr.reduce, the whole data will get loaded in the memory and it tries to execute it parallelly. But whatever loading happened during the execution of an action, whatever loading happened during the execution of an action, that will get destroyed, and if you call this function again, the same process will get executed again and again, and you can see almost similar time is being taken. You can see 0.068 seconds, 0.074403 seconds. So, and that's where, okay, that's where the caching comes into play. If you cache a computation after you have done something while in any of the transformation, then that value will not be recomputed. Okay. All right, that's good, everyone. Great. Now moving ahead. Now this is an example of what goes on in a cluster. All right, this is a good example of what goes on a cluster. Let's imagine that there is a program which is supposed to count the length of lines and summation of all of the lengths, right? Lengths of a line and then summation of all of the lengths. The overall objective is to get the total number of characters in this file, although it can be simply achieved by asking the HDFS. But let's say we want to just count the lengths of the lines. All right, we could be doing many other things, but just for the sake of example, let's just sum up the line lengths of this file. Now, if it is an individual single machine, what happens is when you load these lines from a file, it looks like a big array like this, where elements are separated by comma, and it has got how many elements? It has got 6 elements. And using a map function, if we run a map function on this RDD, this RDD which is on the single node, so what would happen is every line will will be converted into a number, right? Our map function would be returning line length, that's all. So there will be 6 elements here in this, one for each. Then using a reduce, we will be doing the summation of line lengths, correct? Now, in practice, on a cluster, what goes on? In the memory, the process seems very straightforward and nothing to worry. But in case of a cluster, what goes on? When we load the data, some part of the array would be on one machine, some part would be on second one, and some part would be on third one. Correct? And when we execute map function get executed on this node and this node and this node. Right? So when map function get executed on node 1, you get 1091, 1094, and 14 is what you get in node function 2, node 2, and 20 and 4 is what you get in node 3. Afterwards, when you call the sum function on the line lengths, what happens is you total it like 10 plus 9 and 4 and 23 and so on. All right. So on every node, the sum function, the reduce function is combining all these value into a single one. And then, once you get these summations on every machine, then from the driver, what is driver node? The driver node is the one from where the execution is being started. Right here in our case, it's e.cloudxlab.com from which our console is running. This one from this is our driver, and on driver node all the three values from all the three nodes get collected, and again the same function which was summing up these values will be called twice, one for summing up these two, and then one once for summing up these two. And effectively you can see that the function got called twice here, once here, and once here. So 2 plus 1 plus 1, so which means it's 4, and then we have twice here, which means 6 times the sum function is being called on the values in a distributed fashion parallelly, and you're getting the result. Okay, so the whole game about this computation this computation, the whole game is about breaking down your problem into a distributed one. So for example, Ella's question is, I think I missed one question from, okay, here I missed this question. Let me explain this question and then let me answer. There were one more question from somebody. All right. Okay, one quick question. When we use map to execute on each node data and we are storing it in RDD, how internally output is stored? Okay, so internally when we say map, there is nothing happening unless you call an action. And when the action is called, at that point of time, the values are kept partly in the memory and partly in the disk. Mostly values are kept in memory first, and then the computation happens. All right. So yes, at this point of time, the values will be kept in the memory. Okay, good. Now there was one more question. Did I miss anyone's question? So Prem's question is, so if we have multiple nodes, the reduce will be executed multiple times on the console as well as on every node. That's correct. So the reduce function will be executed multiple times on console as well as node 1, node 2, node 3, or whatever nodes on which RDD has been loaded. Okay, so let me take the next question. Good, very great set of questions. Next question from Ella is that based on the info heard so far, looks like Spark is not good for unstructured data such as videos, images, etc. Not really, it's actually pretty good. It is up to you how you break down this video and an image into the values of an array. So let us say you are trying to compute in an image, you are trying to compute the composition of colors. Okay, let us say you have got terabytes of images of a region on the it's a geographical data, and you want to compute how much greenery is there in a particular region in kilometers of data. Let's say you have 1,000 or maybe 10,000 images, which 10,000 images that represent the a city, and you want to compute how much greenery is there. You have these images taken from the satellite, and you have kept these images in the HDFS. So you can load these kind of data, and then using map function, you can read them one image at a time or part of the image at a time, and then you can, maybe using a flat map or or some other way, you can break it down, break the processing of individual image onto multiple machines. Okay, so basically, whether it's a video, image, or any other data structure or any other data, you can always convert it into a big array. That is very, very important. So you can distributedly compute the green component in every image using hundreds of machines, and then you can combine or accumulate together the way we computed average. In the same way, you could do it parallelly using many computers. Or if the computation on every image is very complex, what you can do is you can split the image data into many objects using flat map, and then and then do the computation on, say, uh, every single row in image on one node. So basically, it's up to your creativity how you can convert your complex problem into sequence of maps and reduces or transformations and actions. A question from uh, Ashwin is, where does the data get stored in RAM or like MR in HDFS? So you can store the output of the RDD into the HDFS. Is that your question? Or does your question relate to while in the interim when we are loading data from the files, where does that data go? That data is kept in the memory. Sounds good? All right. So this is how. Now there is a concept of shared memory. Sometimes you want to share certain piece of data with all the nodes in the cluster. Okay. In those cases, you can use broadcast variables. Okay. Broadcast variables are something created using SC, and then you can access these broadcast variable from the from these definitions. So this way, broadcast variable is just like distributed cache. In distributed cache, we were keeping some data. All right. So this is the distributed cache, and the other form of shared memory is accumulators. Specifically, the way specifically when we want to get the data continuously from all the nodes in which RDD partitions are located, if you want to get the continuous stream of data from all of these nodes, then you use accumulators. You create accumulator before you start the process, and then let all the maps and reduces pass the information to this accumulator. All right, so that's the example. All right, a good question from Yogesh. Let me answer. All right, the question is, when you say data is kept in memory, its respective nodes memory, yes. Yes. So when I say that interim while computation is happening, data would be kept in memory, and later point of time it will be parsed. Okay. So yes, it will be individual separate nodes memory. Okay. So sections of the array are located in the memory, and when the computation on the sections happen, the data gets loaded. All right. So accumulators are only those operations in which the order of values do not matter to you, because there is no guarantee of order in the accumulator, because some node is performing faster, so the value could come first, and some nodes are slower, the values would come later. So because accumulate the every element will keep on spitting data to the accumulator. All right, so accumulators could be used for tracking the progress of our maps and reduces. Similarly, accumulator could be used for displaying the logs. All right, so this is our standard word count example. A last question is, can you repeat the value proposition on accumulator? All right, accumulators are used for continuous update. You are sitting here on this node, on this console, and you have launched your maps and reduces. It might take 20 minutes, but you want to show some progress to the user on the screen, that what's going on with this process, how much percentage of the process is complete. In those cases, what you can do is you can keep printing the information using accumulator. Accumulators are basically accumulator is a variable which gets shared across all the map functions. And inside map function, you can push the information continuously to the accumulator, and then you would know that what's the current state of affairs. All right. So here, accumulator is used generally for logs and counters. Logs and progress monitoring. All right, so here is an example, a straight example of word count example, word count standard example here. So we are loading the data into lines using sc.text file. You can see that, and this is the file name which we are passing here. So we call a function called text file on sc, which basically creates an RDD and loads data into lines. Right? It basically, when we execute this, actually it has not brought all the data from RDD into the memory, but it has created a mapping between this RDD called lines and the partitions of big.txt. Now we are defining a function called lines to words. Okay, and what does it do? It basically converts a line, splits a line into an array. Let's try to execute. This is a sentence. You can see that, and it breaks the sentence into array of words. Correct? This breaks the sentence into array of words. That's what this function does. Now here we are saying lines.flatMap. Why we are not calling map? Because this function is converting individual one object into many objects. Not one object into one object, but one object into many objects. So we are saying words equals to lines.flatMap, and we are passing a function called lines to words. And then we have another function called toKeyValue. This function converts a single word. Let's say I pass Sandeep. Okay. Okay, you can see that it has converted it to a tuple where first word is Sandeep and second value is 1. Okay, just like in map we were saying key word 1 and so on. All right, so we are converting a single value into a tuple. Make sense? Next is, let's execute this via map on our words, not line but words. Okay, the one which we achieved via flat map. If you have doubt at any point of time, try checking what does words look like. So we can say take 10. Now you can see that our line has been broken into into one word per object. Make sense to you? And then, all right, so words dot. All right, next is, if you want to check what's there in words kv, you can say words kv dot take 10. Here you can see The one, project one, Gutenberg one, ebook, and so on. And how does that happen? We also did word.lower the while printing the key value. Now we're creating a function called sum, which takes two values, okay, and return the summation of the two. That's how we have defined this new function called sm, which basically takes two values and returns sum. Correct? There's nothing magical about it. Now let's do a newer function called reduce by key. What does reduce by key do? It basically first groups the data by the key. Here the key is this called project, and so on. So the first value in the tuple is the key. First it will group this data by this key, and of then all the values that are collected together would be reduced by using this function called sm. Okay, so this is an RDD which will contain the result of this. Okay, so reduce by key is a transformation because it did not make anything happen. So let's try to make things happen. Now when I say take 1, only then, when I say take 10 on the output, only then the result happened. Here you can see that the empty line has occurred 69,000 times, and scold has occurred thrice, and so on. All right, if you say 200, now you can see more values and so on. Now if you want to save this result in a file, let's call it spark mr output 9 April. It will be saved in the HDFS, which you can check, which you can check here in Hue, which you can check here in Hue. All right. Because this file manager doesn't work for me, so I just go into query editor, then click on file. All right. So here you can see that. Where is my file? Let me sort by date. All right. A question from Yogesh. All right. Question is, all right. Another question from Ray. Let me just show you the output here. So you can see that it has used two reducers and done the job. So here is the output of my key value. All right. So we could also say convert it into another form that's a little more advanced. And while loading, you can use the same way and load again and break it down into things. All right. Now that's a quick rundown of a word count example. Let me try to answer the question of Yogesh. So here the function is taking two parameters to compare the get max value. So here the function is basically summing up two values. How does internal arguments to the function is taken from the list of RDD object? So the way it would happen is here. So here the reduce by key summation is summing up the two values, right? Now internally what would happen is, internally it will first group the data by the key. Okay, the key which was generated by two key value function. So internally the data will get sorted or grouped based on the key, and all the values will be brought together as an array. Now on that array, this function called sum will be executed until all the values become singular value, right? All the values are collapsed into single value by again and again calling sum function on the whole array list. Kulbir's further question is, can we use Spark to read data and process data from HBase? Yes, we can. So there is a HBase input split. We could use HBase input split to load data from HBase. All right, take a look at all the possibilities of reading data from creating RDD based on an input split. All right, now this another example here shows how to use the accumulator and broadcast to produce the results. Let me copy it to somewhere where the font is a little bigger here. So here we are importing regular expression, because in just like we have import function in every other language, Python also need to import regular expression. And here we are saying lines is loaded from this HDFS file. Here this is wrong, so we will instead let's say this. Okay, this is correct. And then we are saying these are the common words which need to be removed. Okay, here this common words need to be broadcasted to all the nodes so that this data appears on every node. Now, using this flat map, we are breaking down the lines into words, and then here there is a lambda function used. Lambda function is anonymous definition of function. Instead of defining function externally, the function is defined in line because we are not going to use the function again. Here we are saying substitute non-alphanumeric characters with nothing and then return word dot lower. Okay, so basically replace non-alphanumeric characters in the word with nothing, and that's what this map will do. Convert the key value pairs after cleaning it. Convert these words into clean key value pairs. Okay, next is here we have a filter function, and everywhere we are adding values to the accumulator in the filter function. So here we are saying before sending the output, please clean the data, and while cleaning the data, append to the accumulator. Okay, append one to the accumulator so that on the accumulator we know clearly how many values have been processed at this point of time. Okay, and we are checking if k0 not in common value, only then return this condition, which means it will return true if this particular word is not a common word. Okay, which means this will filter common words from all the words. And afterwards we say that clean take these many records, and then we reduce by key the way we did previously. This is just for testing this particular line, and then once we have done cleaning up, we print the counts and then save the output in this file. All right, you can try this by yourself. This should work fine, or you can do a little bit more work. You can break it down into proper function instead of inline functions. All right, so here we are using the broadcast variables. All right, a question from Kulbir is there a disadvantage of using Spark over MapReduce? Yes, sometimes a process might consume a lot of memory and not leave any resources for other parallel processes. This is the only disadvantage. But this has been fairly taken care as of now. But still, there are chance of one process consuming a lot of RAM, not leaving space for other process at a point of time. If a developer is not cautious, they might end up consuming a lot of RAM. All right. Now, next part is Spark streaming. So let's take a break for 10 minutes and come back. Break for 10 minutes. Or you want to, because the, yeah, let's take a break for 10 minutes. Back by 9:51 p.m. IST. Hi everyone, can we start now? All right, great. All right. So, so we discussed about all the basic features provided by Spark. There are many more transformations and many more actions that are provided by Spark. You can take a look at their website and in the documentation. So for example, here this one shows all the possible functions provided by Spark library. So you can see all, and then there are sub packages which can be accessed through ML, the MLlib streaming and SQL. Right. So there are many more functionality, so many more actions and transformations provided by Spark, but the basic philosophy remains same. Okay, basic philosophy remains same. All right, and on top of these RDDs and the functions, the other libraries like machine learning libraries or graph manipulating libraries like GraphX are built. So internally, everybody is trying to do maps and reduces in order to solve their problem. On the similar line, one of the libraries that is provided is Spark Streaming. Now, let me first let me first try to explain what does it mean by streaming. What do we understand by streaming? Okay, so streaming is fairly misused word in the industry, and it's basically overused word. So we call movie streaming when we watch movie, and then there is other use case of the word in case of streaming data through a program, the way we had Hadoop streaming. And the third word is Spark streaming, the stream processing. So we will basically, when we talk about Spark streaming, we are talking about stream processing. What does it mean? In a continuous flow of data, when the data is continuously coming to you, you want to process it as and when it comes. So you want to process the data as and when the data comes. So if data doesn't come, you don't process, meaning your processing engine waits till the data comes. Unlike in our MapReduce or unlike our previous examples where we wanted to run our work either by our choice or if we schedule it, we could run it periodically, but not based on data. In case of Spark streaming, or any streaming, we want to process the data as the data comes in. All right. So the process waits until the data comes. All right. So these kind of systems are very interesting in nature. The usual programs where we run a program, it reads some data, does some processing, and saves the data. That's the usual program, right? Those kind of programs are easier to test. We provide certain input data, let the program run, we test whether the output data is matching our expectation or not. But if you are testing a stream processing, you're testing an engine which does the stream processing, testing is fairly difficult because this program never stops. It waits, but it doesn't stop. All right, the way it generally is tested as a example is that we put something called a poison in the input, and then the program gracefully exits as soon as it encounters a poison. All right, so that's another totally another debate. Now now in the stream processing, we process the data that is continuously coming. Okay, if data is not coming, it does not mean the program has to exit and stop and do the cleaning up, but it keeps on waiting for the input data, so it doesn't stop at all. So for example, the data could be coming in various forms like queues. Queues are a very good invention of the enterprise industry, where where we put the data in a common queue and various program reads from the data. All right, I'll take a few examples. Let us say we are building a sign up flow. A user has signed up, and after the user has signed up, you want to send emails, you want to send information to the audit team, and you want to do other kind of processing. Now, a way could have been that we create a single program which checks if the user is coming in. User has finished signing up. As soon as user has signed up, then that program fires uh, other logic. But that's not safe because the user, while signing up, will have to wait for your results, and it's not flexible because tomorrow if there are 100 more processes added to the user sign up flow, then it'll become complex unnecessarily. Therefore, the invention of queue or enterprise event bus, there are many names for the same thing, and there is a queue called SQS from Amazon. So I was doing SQS processing at Amazon, whereby my data was continuously coming in the queue, and I was processing it using around 60 machines. And so similarly, here also, the data which we process as part of streaming comes in queue, or it reads continuously from somewhere. The way our Flume agent keep working day and night, right? In the same way, Spark streaming engines keep working day and night. All right. Now, there are many kind of queues. There is one Kafka, 0M queue, and there could be custom flow of data, such as downloading data from Twitter, or there could be engines like Flume which produce the data continuously, or there could be engines like Tail minus F, that produce data continuously. It waits until the file is written with more data. As soon as more data is coming into file, it prints on the screen. Okay, so the common theme about the inputs to a stream processing engine is that it makes the engine wait, and if there is no data, it doesn't exit the process. All right, so Spark streaming keeps reading data from these queues or these sources, or maybe it's reading from an HDFS folder. It can read from HDFS folder. It can wait on HDFS folder as and processes a newer file which is created in a folder. All right. So Spark Streaming can read from many sources like this, and then after it has done the work, it will save to many other kind of places. Now, what is inside Spark Streaming that we need to understand what goes on? So Spark Streaming, the basic API, the layer on top of basic Spark, what does that layer do? It basically reads data from the input continuously and create batches. And these batches are created in RDD. It keeps on reading the data from input, and for every second or so, whatever you define, it will create batches. And these batches are stored in RDD. Okay, so every batch is kind of made up of some RDDs on which you can run your logic in the way we did earlier. So at the end of the day, if you create RDDs, the streaming engine creates RDDs, and you can process RDDs by writing your code. All right, and your logic, whatever you write for processing RDD, will be executed again and again on every RDD created by this streaming engine. All right, so Spark streaming receives live input data stream, divides data into batches, and Spark engine generates the final stream of results in the batches. All right, so Spark streaming is internally represented as an RDD. Okay, there is a class which does the whole magic. It's called dstream. These streams' duty is to read a continuous data which is coming per millisecond and create batches, and each batch is nothing but an RDD. And against this RDD, all the logic you define will be executed. All right. So, other than that, in case you want to run window-based operation over multiple RDDs, you can do that using something called window operations. All right. Now, I'll just walk you through this example and then you can do the same thing using at your own luxury. So here we are creating a Java based streaming engine. It basically connects, it basically reads data from this service. Okay. And then I think a better idea would be to show you a streaming example, not this. This is not good. I'll show you a better example because we have some time, so we can take a little bit more time and show you a real use case of Kafka. Okay, Kafka is a queue in which we can write data and we can read from Kafka. All right. So since we have some time, so we can um, try to understand more of Spark. All right. So is everybody in for seeing an example of live processing of data? Yes. Great. Great. All right. So first of all, what we are going to do is we create a connection to the queue. Again, let's take a look at the diagram parallelly. Okay, this is a proper example. So here, so we are going to first connect to any of these services. And here in this case, it's Kafka. So Kafka is a queue in which you can push the data and you can read the data. Kafka contains something called topics because in an organization there could be multiple queues, right? So instead of creating everybody creating their own instance of the Kafka, everybody creates their own topic. They talk about a topic and they write about a topic, other people read about a topic. All right. So here we are going to create a connection to the service. First of all, so I'm going to write a program. So since this program is going to get executed again and again by Spark, I'm going to create a separate file in which first I'll import whatever streaming context I need. So other than the Spark context, the standard SC, I'm going to import the streaming context. And first from the Spark context, I get SC, and then I create an object called Spark streaming context. This is the entry point for streaming engine. Now using SSC, I open a connection on this port. I open a connection on this port, which means it would go and connect to this local host and read from this particular input port. Now, it would expect that there is a service running at this port and doing the magic. So we will have to run a service at this port and which will output the data. And afterwards, so we have created this lines. Lines is not RDD. Here, lines is kind of a D stream, okay? Because lines will be created on 1 second data, because here we are saying create a streaming context on 1 second batch. So it will read 1 second's data from input, create a batch in RDD, and on top of that batch, it will create a temporary RDD like lines. Okay, this lines represents that 1 second's data. Okay, next is here we are saying lines.flatmate. Don't be I mean, although it looks like that lines provide all kinds of functions which RDD provides, but lines is actually that 1 second's RDD. Okay, internally it's basically a D stream which is delegating the work internally to the temporary RDD which will be created in future. Okay, so we are saying words equals to lines flat map, just the standard word count, and then we are saying pairs, and then we are counting the words, and afterwards we are printing those words. This is something unique about Spark. This is something very unique about Spark streaming, because this pprint is not there in the standard RDD. Okay, because this is a D stream. It's basically internally it is going to note down all the commands you are giving on the D stream, and it is going to execute these commands like flat map, map, and reduce by key on every second's data. All right, and after we are done with all of this coding, we say ssc.start. Now it will connect to the service which is running on 999 and wait for input data, create batches, and do the logic, and it'll await for termination here. All right, now so we will create this file called spark streaming example.py, which contains everything. So here let me exit from the console. Okay. So here I have written the code already. It says from here import all of this information, and then uh, um, uh, produce the word count for that D stream, and then print that 1 second data. All right. Now, so there are two parts to it. One, somebody who is going to listen to the data, read the data from the input, and somebody who needs to produce this data. Okay? Somebody needs to say. So for saying, we will start a server which will listen on this port and produce some data, and somebody who is going to listen. All right, right now interestingly we are not doing it over Kafka. We are doing over the standard input stream here. Okay, in the same way, the way we are connecting to the input stream at this port, we could connect to Kafka and read the data from Kafka. And the same way, the way we are going to listen at this port, we would generally push the data into the Kafka queue, and that will be read by our Spark streaming and will do the job. Okay, so here I'll show you the example. So the way we are going to run it is very simple. We are going to say Python. We are going to say Python and this command. All right. So this is the file which we are going to run. We are going to say not like this. We're going to say Spark submit. Spark submit executes a Spark program from command line. Okay. So we are saying Spark submit, and it's not able to connect to the port right now. All right. It's trying to connect, but it's failing. All right. Now let's create the service which will run on 999 port, and let me open another console for the same. All right. So here we go. Where is my lab credentials? And then I open another console, and this console I'm going to input my login. All right, so here is my console, but it's not doing anything. Now let me try to run 999, not like this. So I'm writing data here, which is going to be produced here. Now you can see that it has started reading data and started to do the computation. All right, now let me try to produce something really huge data. I'm going to say yes again. You remember yes command, which produce yes again and again. And you can see here, this is reading the data from there and produce and doing all kinds of processing. Okay, Now it has started doing the process. Let me remove the noise. Okay, and how do you remove the noise in case of, how do you remove the noise? By redirecting the std out, or let me say, all the error things, or it was that I had already written a command for this. So I'm going to redirect all the error input to dev null and run it. Okay, so I've started my streaming engine. Let me check if it is running. Let me run it again. All right, so here it's basically printing the Ys per second produced by yes command. On one end, on the other window is producing lot of y continuously, and here it's grouping them, doing the word count of input and printing it on the screen. So you can see that it's producing around 5.5 lakh Ys per second. It's producing around more than 500,000 characters a second, or 500,000 pings a second, and we are able to do that count in a very graceful manner. Yes, everybody with me? Any questions at this point? Ashwin's question is, yes, is it producing in the same node? Not really, it's utilizing the cluster right now. So Spark streaming engine is reading from my yes command, nc command. Nc command is reading all the things which are inputted to it by the way of yes. So all the yeses, all the y's are being read by the d stream continuously per second, and for each second it's creating one rdd. And that means when we create an rdd, it is going to go to Spark, and then it's going to get distributed, and then when we run all other commands, it's going to run in a distributed fashion and then give you the results. All right. Good. So a question from Ashwin is, but in the config you have given on the local host. Yes, that's correct, and that's a very insightful question. Yes. So because local host is only available on this machine, right? So what exactly is happening? The streaming engine, the D stream, the creation of the reading of the data is only happening on this machine. Many machines are not reading the data simultaneously. Only this machine, the local machine, is reading the data and then creating the RDD on top of it. Kulbir's question is, which BI tool can we use for real-time analytics? Honestly, the kind of real-time we are talking, none of the Tableau, so although Tableau and what do you call, Tableau and other BI tools like what do you call, the what do you call, D3JS, you can use any of these kind of real-time, you can use any of these graphs. So Tableau is something which does the job, but I'm not very confident. Okay, so the way you can do here is the way the industry does the real-time dashboarding is that on one hand you are running your Spark streaming cluster, which is continuously updating data in relatively static form, say in your MongoDB or in your MySQL. So Spark can write to MySQL. So the results of Spark streaming can be saved in MySQL, and from there your program, whatever is the program, can read from MySQL and display it continuously. All right, so there will be a refresh rate on the screen, and during the refresh it will basically reload the data from the MySQL, reload the results from the MySQL, while on one end Spark streaming will continuously update the data in MySQL as and when the process gets computed every second. Ravi is saying that you can use Informatica tool. Ashwin is saying you have told data is produced in the cluster. What about data produced in other node is gone? Yes. So here the way we are producing data is very localized. Okay. So therefore, when you have data produced by many more clients, you use a proper queue. Here we are using a TCP IP connection. A proper queue is that there will be a there will be a big queue. Okay, you can think of a big queue in this form. All right. On one end, from one machine, there will be many people writing to it. On the other end, people will be reading from it. Okay. So there'll be many data packets being saved by all these clients. And on the other hand, the people will be reading from this queue. Okay. Although these will be separated based on topics, there'll be one topic and there'll be another topic in this. All right. So many people can read and write to the queue, and that's exactly where we put the data. That's exactly why we put the data in the queue, in which many servers, server 1, node 1 IP address, 2, 3, 4, and 5, they all can write to the data. And on the other hand, Spark streaming could read from it, or maybe some other engines could read from it, maybe HDFS. This stream could go to HDFS, and so on. This stream could go to HDFS. I'm pretty bad at writing, so yeah. So that's where the queue comes into play. Good question. Make sense to you, Ashwin? All right, great. Okay, did I miss anyone's question? Good, brilliant. So this was our example for streaming. Okay. So in the similar fashion, we could create data in a Spark queue, and in our Spark streaming at this point, okay, at this data will be also available in HDFS probably. Okay. So here in this, there would be a folder called Spark. In this, you will find this Spark streaming along with the command. And there is uncommonwords.py, which contains our logic for finding a logic for finding the logic for finding the logic for finding the uncommon words count. All right. A question from Ella. Question is, can you quickly show an example of Spark SQL? All right, I don't have one right away. I might have to look into Spark SQL and data frames. All right, so all right. So basically, the way it happens in case of Spark SQL, you can load data from JSON and anywhere, and then execute query on top of that data. All right, this is data frame manipulation. So you can see that we could load the data using Spark context and execute queries from there. All right. I am not sure if I'll be able to give the context right now, but what I can do is I can share a Spark SQL video that will make more sense to you because it goes with one step at a time and moves ahead. All right. Okay. All right. So that was a quick overview of Spark streaming. Let me put in my to-do. Number one to-do is move updated slides of Spark streaming, and another to do is share the Spark SQL video on the course page. All right, so I think that will do that. All right, so yeah. All right, I'll just take you quickly through various available databases, available systems, so that while making a call on any big data systems, you have a quick idea about what does it do, so that you're not confused about the systems. All right. So the way we just now did the computation per second, if you have to do the computation per milliseconds or lesser, Apache Storm will be a better option. Spark streaming is great, but does not work well if our expectations are below 1 second batches. But in case of you want to do the same thing what we just did on millisecond or say lesser than 1 second, say you want to create 10 milliseconds or 100 milliseconds batches, or you want to print that less than half seconds, then Spark streaming would not be much useful. Instead, a system like Storm will do the job. So it reliably processes unbounded streams of data. It can be used with any language and is fairly fast. It can approximately process 1 million tuples per second per node. Okay, and it's fairly scalable and tolerant and guarantees that your data will be processed. Okay, integrates with queuing and databases technologies, and it has been in use for quite some time, and so many companies had been using. Before streaming, there wasn't a really good solution available for streaming, for stream processing. Okay, now a quick comparison between Storm and Spark. The processing model of Storm is record at a time, and Spark does mini batches. Latency in case of Storm is sub-second, while in case of streaming, it's few seconds. And fault tolerance is whether every record processed or not. In case of Storm, a record might get processed twice, but never get missed. In case of Spark, it only get processed once. Okay, because Storm has to guarantee the sub-second kind of a latency. So when you handle that kind of latency, a small latency, and tries to produce a fast result, a better decision is to let something get processed twice rather than get missed. Okay, that's the decision Storm has taken. Implementation and API. The origin of Storm was at Twitter, and Spark streaming was at UC Berkeley, and Storm was implemented in Closure while Spark streaming was in Scala. And Storm was written in Java, while Spark Streaming was written in Scala, but now Python and Java as well. So Storm does not have a batch framework integration, but Spark Streaming has internally Spark batch framework. Because we call that also batch framework because it runs when on the demand, not in the stream processing manner. Now, with respect to production support, Storm is being in production since 2012 11, and it comes with Hortonworks HTTP, while Spark Streaming comes with Cloudera and Mapr, although we can install, so we have installed it by ourselves. And now, the company, there is no support, there is not great support for Storm, while for Spark Streaming, a company called Databricks provides continuous support. Resource Manager integration, Storm can run on Mesos, while Spark Streaming can run on Yarn and Mesos. Actually, Storm has started running on Yarn as well. All right. Now, quick summary is the red flag with respect to Storm is the support available, while red flag with respect to Spark Streaming is the sub-second kind of processing. So, as a thumb rule, if you want to do a sub-second kind of processing, if you want to process records, your batches are less than sub-second, lesser than zero point 0.1 second or less than 1 second, then you go with Storm. Otherwise, you continue with Spark. All right. You can do a further study at this point. All right. Now, all right. I will just, yeah. Kulbir's question is, can you give an example of Sparkar? Sparkar is similar to what we have discussed. So instead of using maps and reduces, you basically execute the computation on the data frames. All right. Right now, I don't have an example of Sparkar. All right. Since Sparkar is kind of launched in February, I mean the stable version was released, I think March or February. So it's actually not yet available in the cluster. We had installed separately as well, but I'm not sure if it's running or not. So let me see. User lib. No, we don't have. So, all right. I think it's a time to upgrade Spark. All right. I think I have installed here. Here. So you can actually run. All right. Looks like it needs Scala as well. Let me check it later. Okay, so we can load the data frames and do the logic. All right, so here we can load the data and then start working. The way we used to do is, all right, I'll need to just take proper example. So you can actually, yeah, you can use the R if you want to do. All right. Okay. So I mean, I don't have a pre-prepared example because otherwise we could have just loaded the data using R and manipulate using data frames. So the way you can do, you can use SQL to transform data, select columns, and then run certain operations. In the same way, you can create a data set in R and then intersect it, remove certain column, keep certain columns, and so on. You can do all those operations. You can try using it. Follow any simple Spark R manual. That should be good. All right. Now coming back to Redis. So Redis is basically an in-memory database. So I'm going to compare quickly what are various NoSQLs so that you have a quick idea about what are various systems. So Redis is basically an in-memory database. Although the data is saved in the disk, but it keeps in the memory. So it requires huge RAM. All right. So if you know that your data can fit in the memories, in the RAMs, then Redis is a good solution for you. So it's for rapidly changing data with foreseeable data size. It should fit mostly in memory. For example, to store real-time stock prices or real-time analytics, leaderboards, or real-time communication. And wherever you used Memcache before, you can use Redis. All right. So the advantage of Redis is that the write and reads both are extremely fast, and therefore all the places where you have smaller data but reads and writes are needed really fast, in those cases you can use Redis. You can use a document oriented database such as MongoDB if you need dynamic queries, and if you want to create indexes, such as you want to look up on address, you can want to look up on first name, then you can use MongoDB. What is document oriented database? Document oriented database, instead of storing row as a list of values, the row is a complex object in a document oriented database. A document, the way MongoDB defines, is essentially a complex JSON object. The JSON object could be as complex as the one which is being displayed on the right hand side. It has first name, last name, age, which are strings and numbers, while address is another object which contains further values, and these could be further more complex values. So MongoDB supports the complexity up to 100 inner objects, like objects within objects. All right. Ashwin's question is, in the place of HBase, can we use Cassandra and MongoDB? Yes, you can use. All right. But if you already have Hadoop cluster, you should prefer using HBase. So MongoDB provides you a similar aggregation, similar kind of filters like SQL, but it doesn't provide that powerfulness of SQL, but you have to write MapReduce in case you want to join two data sets. Okay. So if you wanted to use CouchDB, but your data, your changes are too much and filling up disk, then you go for MongoDB. For most of the things that you can do with MySQL or Postgres, but having to define a constrained schema is holding you back, in those cases you go for MongoDB. Meaning, when your website grows complex, when your objects become really complex and you want to keep them complex, then you go with MongoDB, because not always you can flatten things and make relational databases. All right. Next is the Cassandra. It is good for storing huge data sets and in the almost SQL kind of fashion because it provides you a query language. When you use to store huge data, so huge that it doesn't fit on one huge server, still, and still you want a familiar interface like SQL, then you go for Cassandra. So Cassandra is almost like HBase, but Cassandra has a query language while while the Cassandra has a query language while HBase doesn't. All right. So HBase is great for billions of rows by millions of columns. It's great best use when Hadoop is still best way to run MapReduce jobs on huge data. It's best if you use Hadoop. If you already have Hadoop and HDFS kind of stack, then you go for HBase. Now, all right. I'll answer your question, Ashwin, in a minute. So another thing is that all the search engine where you are talking about petabyte bytes of data, HBase is a better solution. Okay, similar to HBase, you have Accumulo and Hypertable. If you want cell level protection, then you go for Accumulo. And if you want to store smaller data but with the same philosophy as HBase, you go with Hypertable. A more detailed overview is available at this point. Okay, at this URL. All right, all right, all right. There are two questions. One is from Ashwin, what is Mesos? And other is, okay, other is what is Impala? And there's a question from Yogesh. What do you mean by cell level security? I'll answer the last one first. So what do we mean by cell level security? So if you remember and if you try to do HBase, you can actually manipulate everybody else's table. You cannot define kind of rules that only these people can access these rows or these particular range of cells are only available to these users. If you have to do that in HBase, you will have to write coprocessors, right? So instead of writing coprocessors, if you need a cell level protection, you can use Accumulo. All right. Now, next question is, what is Mesos? Mesos is nothing but it's a resource manager just like Yarn. Mesos helps you get things done in a cluster on various machines. But Mesos itself doesn't do anything other than executing the programs in the cluster, just like Yarn. Yarn tracks the various resources available in the cluster and then executes the proper code accordingly. Similarly, does the Mesos. Mesos also tracks the resources in the cluster and when you want certain resources from the Mesos, it can provide you and tell you which machine to go to. All right. So what is Impala? Impala is basically a quicker way of executing SQL queries on the cluster. So Hive engine can be improved by using Impala. So that's pretty much about the course. All right. Now I would like to take you through the project discussion. All right. So the objective of this exercise is to do the sentiment analysis based on the tweets. Okay. So Yogesh's question is, can we call Impala as some extension of Hive? I would say we can call an alternative implementation of Hive, which is little faster than the usual Hive. All right. So it's basically kind of competition between Hortonworks and Cloudera, which has resulted in an engine from Hortonworks and an engine from Cloudera, which are basically little faster than the traditional Hive. Okay, now let's talk about the project, the overall project. So this objective of the exercise is to do the sentiment analysis on the tweets data downloaded from Twitter. The steps below outline the primitive strategy, but these outline the primitive strategy, but not necessarily. Okay, so not necessarily the answer, it's just an example approach. Okay, it's up to you to choose exactly same steps or use a different strategy altogether. The various deviations are possible. For example, you could use pig instead of hive. I've used hive in this example. You could use pig instead of hive, or use a completely different algorithm to compute the sentiment based on, say, natural language processing. Or you could use your own Flume pipeline to download the data. Here we have pre-downloaded data. And also you can start afresh with a different movie. Here we are using a movie called Iron Man. You could go for any other movie. And create your own program to download data from Twitter instead of Flume. These are the various deviations possible. Fifth is, instead of instead of displaying data, you could use D3JS, Tableau, or BERT to present data. Here we are using Excel to present data. So Alan's question is, could we use R for the visualization based on a more complex Hive query? So what we can do is, if that is your case where you have a big query and you want to present the data using R, what you can do is, using Hive, you can produce the results, and then those results can be loaded using R, and the data can be displayed. But R right away cannot be used to process complex data, a huge data, because R works in RAM, and in case you are loading everything into R from, say, HDFS, it's going to overflow the memory. Okay, so if you want to use R directly in the processing, you could use stream processing and supply R script as argument for mapper and reducer. Great. If you, yes, that's good. Alan says that I'll use Hive for heavy lifting. Yes, that would be the right way. So you can save in Hive server, and from Hive server, you can load data into R. R provides all kind of readers. A question from Ella is, any tips on how we can get the data for another movie? Check the Flume config. Okay, I'll show you everything. And all right, now if you log in into Hue, the data would be in this particular folder. Okay, the data would be in this particular folder. if you Kulbir's question is, should we use Spark R instead of R? Yes, you can do that. If you have to do the real heavy lifting, you could use Spark R. But again, visualization part is missing in Spark R. All right, let me just go to the file browser, go to top level, data, and then inside data, you have sentiments file. Okay, and inside sentiment files there is another sentiment files. So there you will see upload and data, and if you come back here, so there is the Flume folder which shows you the config related to downloading data along with the custom sources which contains the Twitter download. Okay, and then if you go here, it shows you two folders. One is data and other is Hive. Hive contains the query that is required for processing data, and data contains the actual data that is needed. It contains three folders. One is dictionary, second is the time to country relationship, and third data folder is Twitter raw data. It contains the compressed zip folder. Okay, this basically most of the whether pig or hive both are capable of loading compressed data from hdfs, and this capability is inbuilt in both of them. All right, so let's take a look at this particular query. All right. All right, let me just take a look at. Okay, just a second. Okay, actually, the correct query is here, data and sent. Yeah, this is the query. Okay, so this is the query which we have recently changed. So we have not changed the old one. We have made certain modifications according to the newer versions of Hive. So first is you can copy it to the local, or you can actually do add jar and put hdfs directly here, saying hdfs colon and then this folder. Okay, you can directly do that. Okay, and then you can create your own database in Hive with your own name, and then you can use that database before you start the process. Okay, so first of all you can do the add jar, and instead of copying it to the local folder, you can simply say add jar hdfs colon slash slash and then this folder. Okay, so I can show you this. So if I am in Hive, so I could say add jar hdfs colon slash slash. So this way you can add the resource. All right. Okay. Next is that you have to turn off the reserved keyword, otherwise it will give errors related to the users. And then you create a table called external table, and basically it should point to your data, and you can copy the data to your folder, and then you can create a dictionary external table. And afterwards, once you have created these three tables, these are external tables, and then you can create tweets clean by first breaking down the timestamp and converting it into the country, breaking every tweets into the word, and then comparing each word against the dictionary, whether it's negative or positive. And then you can join. You basically go through the query. It should give you a very clear idea as in what's going on here. So here we are, as you can see that we are first breaking a sentence into words, and then after we have broken the sentence into words, we are we are joining that with the dictionary and comparing each word against dictionary, whether it's negative or positive. And then and then here it's a join, not left join, or you can see it's a left outer join, not other way, because all the words are needed in the output. And afterwards, we are summing up all the polarities of each word, which we found from the dictionary. And if the polarity is greater than 0, we are calling the tweet to be positive. If the polarity is summation of all the polarities of all the words in a tweet are less than 0, we're calling them negative. Meaning, we are first grouping the data per tweet and then summing up the polarity of all the words in that for each tweet, and then terming each tweet negative or positive. And once we are done with that, we are saving the result into a table which can be presented which can be presented in the form of uh, a table or a graph. A question from Ella: if we did not have the data structures available for Twitter data, how would we go about understanding data structure to define the table? Okay, you can only do that by looking at the data. If you look at this data here, um, let me go ahead and create this data. So if you go into tweets raw, here is the format that will give you clear idea of what format is it. It's a JSON format. We are trying to load this JSON data as a table. So this dictionary is a standard dictionary, Aswin, which contains the uh, word and the polarity. All right, it does not contain word and the meaning. It contains whether a word is negative or positive. All right. Okay, Ella, let me take a look at the vertex failure error. All right, so once you have gone through and understood how this Twitter table is being generated, you can install Hortonworks Excel driver. Here at this point, make sure that you are installing, you first find out which Microsoft Excel you have. If it is 64-bit, install 64-bit driver. If it is 32-bit, then install 32-bit driver. Please check your Microsoft Excel because you're installing Excel driver, so it has to match the architecture, whether 32-bit or 64-bit. All right. Once you have done that, you can create a ODBC setup by following this guide. And here you can provide your host name, username, and password to connect. If you open this file, this guide, it will tell you how to install Hortonworks driver and then configure the ODBC driver setup. So you can give your login and the password and the host name. And once you have done that, you can click on the test button, and then you can start creating the reports. All right, just follow this guide and it will help you with all the steps. All right, so It's a quick exercise and a simple exercise, but it'll take you through the complete cycle of doing the analysis and visualization of big data. All right. So that was pretty much everything about the course. Please go through the exercise about the project. Also finish all the assignments as part of the course and submit all of those. Okay. Now, okay. So that's pretty much. We have. I would like to unmute you all for a minute, and if you have anything to say. A question from Ella. Question is, based on your experience and what you have seen, can you share the industrial view on various tools we have learned? Scoop, Flume, Oozie, Pig, and Hive. So Scoop basically used for copying data from SQL to now, SQL to HDFS. Flume you use for stream processing or continuous data uploads. Oozie you use for overall workflow, and Pig you use for uh, querying the data, and Hive you use for again querying the data. So based on my experience, what I found is people use most of these tools which are related to SQL more. For example, Hive and Scoop will come into more use, while Flume, Oozie, and Pig remains as developer tools and are rarely used. Okay, so that's the so I would say that more popular are Hive and Scoop than Pig, Flume, and Oozie. All right. It's very difficult to, say that which tools are important. We have considered all kind of tools that are generally used, but out of my experience, most of the people choose Hive. But those people who know Pig, they prefer Pig over Hive because they find the Pig query language easier than Hive. Okay, so a question from Prem. Here we have documented the step. Suppose we have a problem set. How we can think of the logic to come up with approach. Okay, so the general way is to attempt to solve the problem with a querying language such as Pig and Hive. If you can't solve it and you have some custom development to be done, you generally go with an approach whereby you create the UDF for Hive for specific problems. And then in the worst case scenario, when your problem is really complex and you can't find a way to solve it using Hive, you generally then start with MapReduce. Also, you have to understand whether your incoming data source is continuous and what kind of latency we are okay with. All right. If you want to do a continuous computation, then streaming is required. If you just want to push the data from a continuous incoming stream, you generally are good with Flume. Otherwise, and rest of the tools we have already discussed. So so I think the defining if there is a single strategy for logic, that would be fairly difficult. The only way to come up with the logic is understanding the limitations of the tools and understanding the capability of tools, and then given a problem, you can always translate it into some form of the language or some form of the logic to apply. All right. So that was, yeah. Okay. Any other questions at this point? Great. So it was a great class. And All right. So it was a great class, and I'm really thankful for wonderful questions. And keep the questions coming, even though the class has ended. The relationship is far longer because it doesn't make sense in today's time because everybody gets connected to me over LinkedIn. So feel free to connect over LinkedIn, and also it'll be great if you write a review on Quora or Facebook. That's a kind of reward for us. And feel free to get in touch with us if you have any questions. And we will send you a form whereby we collect your resumes if you're interested, so that we know exactly if you're interested in working with us. Uh, we will send you a form. You can mention there. All right. So that's pretty much from my side. So please submit the project, and as soon as you submit the project and assignment, we will send you the certificates, and stay connected. A question from Ella, and no, question from Ritika, and others. So you can actually log into cloudxlab.com, and there it shows the extended date. For me, it's September 29. And in case you want to extend, you can click on extend now, and you can take. All right. So, all right. So, okay. No worries, Abru. Whenever you have time, please submit the assignments and exercises. Okay. So Ritika, you can see the Cloud Lab access here, and in case you want to extend, you can extend. A question from Ella. Can we ask you questions till the project? You can keep on asking the questions, no worries. All right. And Ritika's question is, since today is the last day access, so please check with that. All right. For you it will be different. For me, it's till September. All right. So I will. It will generally show where in the page. Okay. So that's pretty much from my side. So we will share you the link to the Quora reviews page and the Facebook page, and there you can share your review as well as get connected to me. You can search for Sandeep Giri. And now that Google has started suggesting Hadoop next to my name, you can see that. Okay, so you can look for my profile, and then, all right, all right, you can get connected, and also stay in touch so that you have questions or we have some upcoming work, we can connect with you. All right. So thank you everyone, and have a great time ahead. Thank you, Yogesh. Thank you, Alan. Thank you, Ritika. Thank you, Abru. Thank you, Ella. Thank you, Ashwini. Thank you, Ravi. Thank you, Kulbir. Thank you, Prem. Thank you, Finny. Thank you, Ashwini. Thank you, Ashwin. It was a great session, great set of questions, and quite enriching for myself. All right. I'm happy, Ritika, that you find the learning as great experience. And all right. All right. So have a great time ahead. Bye bye.